Now, if you look at the steam table, you may notice that our published values have a pretty large gap in between them, especially in some higher value locations. So what happens when we are interested in a value that exists between two published values? We are going to implement something called linear interpolation. And linear interpolation assumes the slope between two known points, that is, our slope between two published values in the steam table, is linear. And therefore, any point on that line in reference to these two published values will create a line of the same slope. Linear interpolation is easy to visualize. Let's say we're interested in determining our saturated liquid specific volume at a pressure of 5,328 kPa. If we look at our saturated water pressure entry tables, we notice we have an entry for 5,000 and 6,000 kPa, and our saturated liquid specific volume at 5,000 kPa is 0.001286 meters cubed per kg, and that at 6,000 kPa is 0.001319 meters cubed per kg. That is, if we plot our pressure versus our specific volume, we have 2 points. Now the slope of this line, our rise per run, is our difference of pressures, 6,000 minus 5,000 kPa, per the difference of our specific volumes, 0.001319 minus 0.001286 meters cubed per kg. Now to find our specific volume at a pressure of 5,328 kPa, we will plot that pressure value on our line, which exists between 5,000 and 6,000 kPa. M prime is going to be equal to our slope m. M prime, expressed mathematically, is 5,328 minus 5,000 kPa over our specific volume of interest, nu, minus our lower bound, 0.001286 meters cubed per kg. Now, if we set the right-hand side of the expressions for m and m prime equal, we have m, which was equal to 6,000 minus 5,000 kPa per 0.001319 minus 0.001286 meters cubed per kg is equal to m prime. 5,328 minus 5,000 kPa per nu minus 0.001286 meters cubed per kg. Or if we express this in terms of ratios of rises and runs, our left-hand side would be dimensionless, where we'd have our ratio of our rises. 5,328 minus 5,000 per 6,000 minus 5,000, and this has a quantity of 0.328. Our right-hand side contains all our information related to our specific volume. We'd have nu minus 0.001286 meters cubed per kg per the quantity 0.001319 minus 0.001286 meters cubed per kg. Therefore, if we solve for a specific volume, we'd have 0.382, our non-dimensional coefficient, leading the denominator on the right-hand side, which was 0.001319 minus 0.001286 meters cubed per kg, plus 0.001286 meters cubed per kg, and we have a value of 0.001297 meters cubed per kg. And we see this value exists between our two published bounds. 0.001297 is clearly between 0.001286 and 0.001319 meters cubed per kg. If it is not, you have a mathematical error. It is noted we can only interpolate between values on our table. We cannot extrapolate. Let us consider an example where we want to find our saturated vapor specific volume corresponding to a temperature of 32.5 degrees centigrade from our saturated water temperature entry table. To do such, we'll look at our table B.1.1 on page 776, and we see based upon our temperature entry, we have published values of 30 and 35 degrees centigrade. And our saturated vapor specific volume corresponding to these entries is 32.8932 and 25.2158 meters cubed per kg. We see 32.5 exists in between our two published values, and thus we're solving for nu at this temperature. Setting up our interpolation equation, we're going to take our intermediate value, 32.5, less our lower bound, 30. This is per our upper bound minus our lower bound, 35 minus 30. On our right-hand side, we're going to have our specific volume corresponding to 32.5 degrees centigrade, less our specific volume corresponding to 30 degrees centigrade, or 32.8932 meters cubed per kg. Now in our denominator, we're going to have our specific volume corresponding to 35 degrees centigrade, 25.2158, less our specific volume corresponding to 30 degrees centigrade, 32.8932 meters cubed per kg. Thus, our specific volume is found to be 29.0545 meters cubed per kg, and it clearly exists between our two published values. Now say we want to find our specific volume at a temperature of 400 degrees centigrade and pressure of 350 kPa. We recognize that this is a superheated vapor, and thus we have to go to our superheated vapor water tables. If we consult table B.1.3 on page 785, we recognize that we have a 300 kPa pressure subentry and a 400 kPa pressure subentry. Both of these subentries have a specific volume defined at 400 degrees centigrade. However, we do not have a 350 kPa pressure entry table. Thus, we have to construct a subtable. And to do such, we're going to interpolate between pressure at a given temperature. Our specific volume at 300 kPa in 400 degrees centigrade is 1.03151 meters cubed per kg, and that at 400 kPa in 400 degrees centigrade is 0.77262 meters cubed per kg. Thus, if we set up our interpolation equation between our published pressure values, we'd have 350 minus 300 kPa per 400 minus 300 kPa. And this would be equal to our specific volume of interest, less our specific volume corresponding to a pressure of 300 kPa, 1.03151 meters cubed per kg, per our specific volume of 400 kPa, 0.77262, minus our specific volume corresponding to 300 kPa, 1.03151 meters cubed per kg. Thus, we find our specific volume to be 0.902065 meters cubed per kg, which clearly exists between our two published bounds.